Hello, everyone. Today, we will continue with the heat equation. This is the first partial differential equation which we are going to consider in this course. Before that, I'm going to solve one more example and how the Fourier series helps in the ODEs. And then we would go on to continue to study the heat equation. I'm assuming today we would only talk about the setup and the basics and the framework of the heat equation. And only the steady state solutions. And on Wednesday, we would start solving this, this PDE. Okay. Is there any question from previous meetings? If there is anything, you can ask me now. If not, we can start working on these problems. You can always use the complex Fourier series. There is no, so in this case that we are dealing with a real valued function, it's fine. You can use either real Fourier series or a complex one. It's just your choice. They are equivalent. I personally prefer that because that looks more unified. But for you, if it's easier to work with real Fourier series with sine and cosine, in our course, it doesn't matter. For any question which you can use one, you definitely can use the other. It's just your choice. Okay. Let's look at one example. Suppose we have this ODE and we want to solve it. The second derivative of y with respect to x plus 2 times y is equal to, say, is equal to x. Okay, suppose we want to solve this ODE. The point about this ODE is that this is not homogeneous, right? This is a non-homogeneous ODE. So when we want to solve these types of equations, if you remember, first we consider the homogeneous version. So what would be the homogeneous version of this ODE? It means just ignore the terms which they do not have y. So it would be something like this. So the first step would be solving this equation. So in order to solve this equation, we should look at the characteristic equation. So let's down the characteristic equation for this homogeneous ordinary differential equation. It would be m squared plus 2 equals 0, right? So it means m squared is equal to minus 2. Therefore, m is equal to square root of 2 times I. And well, let's call that m1. m2 would be minus square root of 2 times I. We have two complex solutions here. And as you can see, they're conjugate of each other. Because they don't have real part here, one of them is the minus the other one. So the goal is to find a particular solution to the non-homogeneous equation. Okay, so the idea here is to write the Fourier series of everything. Okay. So now we want to find a particular solution to this equation. So the idea is to write down the Fourier series for everything we have in this equation. Okay, we start with x. So let's start with x. So the idea is to write down Fourier series of everything in this equation. So, well, let's start with x. X is the thing we know, y is the thing we don't know, right? Let's start with x. What is the Fourier series of x? So let's say we would write it as a naught plus sigma an cosine nx, where n goes from 1 to infinity, plus sigma bn sine nx, where again, n goes from 1 to infinity. Now we want to compute these coefficients, an and bn, and of course a naught. So the first thing to note is that this function x is odd. Yes, that is correct. I saw that in the comments we also have this note. So x is odd. What does it mean? Well, remember the function cosine and cosine of nx, they are even, right? When we have an odd function, these cosine terms, none of them would appear in the equation. So all of these terms which they have cosine are 0. It means the terms an are 0. These terms do not appear in the equation at all. So we only need to find a naught and bn. Okay, great. Actually, we can kind of compute a naught, or we can just guess what a naught can be. So in order to compute a naught, one idea is, so there are two ways we can do that. One idea is to just write down what a naught would be. So write down the formula for that. F of x, which is x dx, and compute, and you would see this is equal to 0. Or you can just directly say if x is equal to a naught plus sigma bn sine of nx. If we let x to be 0 on both sides, the left-hand side would be 0, right-hand side would be a naught plus sine of 0, which is 0, which again shows a naught would be 0. Okay, so a naught is also 0. So now here x is just equal to sigma n goes from 1 to infinity bn sine of nx. And the only thing which we are looking for are these numbers bn, right? So what is bn? Bn is equal to 1 over pi integral from minus pi to pi fx, which is x, sine of nx dx. Note that here I have chosen the period of the function to be pi. However, the function x, which appeared in the equation, was not periodic, right? This period doesn't matter. We can work with any period we want. I chose pi because it's just easier to work with. It's like we had this function y equals to x. Sorry, f of x equals to x. This was the non-homogeneous part of the equation. It's like I've decided just to look at this function on some interval from minus pi to pi to write down this Fourier series. We could choose any other interval to do these things. It really does not matter. Okay, so that's completely arbitrary. Okay, so we want to do this computation. So how can we compute this one? As you can guess, the best way to do this one is integration by parts. So we should decide what is u and what is dv. So we can take u to be x and dv to be sine of nx dx. So if u is equal to x, du would be dx. And if dv is equal to sine x dx, then v would be equal to cosine nx over minus n, right? So now integration by parts tells us Bn would be equal to 1 over pi times uv minus integral of v du. So uv here would be x minus x cosine of nx over n minus integral of duv, which would be plus cosine nx over n dx from minus pi to pi, which is equal to 1 over pi minus x cosine nx over n plus 1 over n, and the integral of cosine of nx would be sine of nx over n, again from minus pi to pi. So this would be equal to 1 over pi. If we plug in pi, substitute x with pi, we would get minus pi cosine of n pi, which is equal to minus 1 to the n over n, plus 1 over n times 0, sine of n pi is 0, minus, and then we would get pi cosine of minus n pi, which we would get the same thing. Again, plus 0. Right? So pi and pi, they would cancel each other. We would get minus 2 times minus 1 to the n over n. Okay, so Bn is equal to minus 1 to the n plus 1 over n, if there is no mistake in my computations. Hopefully that's the case. Was there any 2 which I forgot? Yeah, there was. It was times 2. So the Fourier series for x would be the sum and goes from 1 to infinity Bn, which is 2 times minus 1 to the n plus 1 over n sine of nx. So let's go back to our equation. What was our equation? Our ODE was this thing, the second derivative of y with respect to x plus 2y was equal to x. That was our equation. Now we know x, we have this other, if we just restrict this equation to the interval from minus pi to pi, x would be equal to this Fourier series which we have here. Okay, so now the idea is that rather than finding a very explicit function for y, like a polynomial, like these sorts of function, we can find the Fourier series of y. So we try to find the Fourier series of y. And this would be a particular solution. So in general, we can write down y as a constant. Because we have used a naught and b naught, let's use some other constants. Let's say c naught plus sigma c naught cosine nx plus sigma, sorry, it's cn, plus say dn sine nx. Now the derivative of y with respect to x would be equal to, now if we have this description for y, remember if we have some assumption on convergence of these series, we can take derivative term by term. So the derivative of c naught would be 0, the derivative of first sum would be equal to sigma n goes from 1 to infinity minus n Cn sine of nx plus the derivative of the second sum would be n dn cosine of nx. Our equation actually is related to second derivative of y, so we take the second derivative of y with respect to x. Again, we take derivative terms by terms. So we would have this sum, n goes from 1 to infinity, minus n squared Cn cosine of nx, plus minus n squared dn sine of nx. Okay, so the left-hand side of our equation was the second derivative of y with respect to x plus 2y, right? Now this is going to be equal to, well, we computed that, right? The second derivative of y was sigma minus n squared Cn cosine nx plus sigma minus n squared dn sine nx. Plus 2y. What was y? Well, we had also that. It would be 2c naught plus sigma 2cn cosine nx plus 2dn sine nx. And this would be equal to, well, we have the constant 2c naught plus sigma minus n squared Cn plus 2cn cosine nx plus sigma minus n squared dn plus 2dn sine nx. This is the left-hand side of our equation. Now it is supposed to be equal to our right-hand side, which was x, but x was equal to sigma 2 times minus 1 to the n plus 1 over n sine of nx. Now, this is quite interesting. This gives us three equations. So if what we have here is supposed to be equal to what we have here, the constant on both sides should be equal. The coefficient of cosine of nx on both sides should be equal. And the coefficients of sine of nx on both sides should be equal. So on the left-hand side, we have the constant 2c. On the right-hand side, the constant is 0. On the left-hand side, the coefficient of cosine of nx is equal to minus n squared Cn plus 2Cn. On the right-hand side, the coefficient of cosine nx is equal to 0. On the left-hand side, the coefficient of sine of nx is equal to minus n squared dn plus 2dn. On the right-hand side, it is equal to 2 times minus 1 to the n plus 1 over n. Okay, we should use these equations to find out what are the values for C naught, Cn, and dn. Okay, let's look at the first equation. Well, that's the trivial one. That implies C naught is equal to 0. So in the description for y, there was no C naught from beginning. That's 0, right? That's the equation number 1. Let's look at the second equation. I would write it here. We have minus n squared C naught plus 2C naught is equal to 0, which is equal to 2 minus n squared times C naught equal to 0. Well, the point is that 2 minus n squared is always non-zero, right? N is a natural number. N squared is not equal to 2. Therefore, what we have here is non-zero. So we can divide both sides by 2 minus n squared. Therefore, Cn is equal to 0 for all n. right? So all the terms Cn are equal to 0. The only remaining part is the part for Dn. So the left-hand side is equal to 2 minus n squared Dn. The right-hand side is 2 times minus 1 to the n plus 1 over n. If we divide everything by 2 minus n squared, we would find what the n is. The n is equal to 2 times minus 1 to the n plus 1 over n times 2 minus n squared. That's the value for the n, again for natural numbers n. Is there any question here? Okay, so why was satisfying this? Well, why is satisfying this equation? And we now can see, if we just look at the interval from minus pi to pi, we would get a solution of this sort. Well, it would be 2 times minus 1 to the n plus 1 sigma minus 1 to the n plus 1 over n times 2 minus n squared sine of nx, and goes from 1 to infinity. Okay, that's one way of answering this problem. So this is a particular solution. So the general solution would be the homogeneous one we found plus the particular one. Okay, great. Okay, maybe now it's a good time to start chapter 2, the heat equation. Okay, I should say these chapters, well, this chapter and also the next one, they have a mathematics side and a physics side. And I do not know much about the physics side. And you also, for this course, you also don't need to know that. At least here, we just focus on the equations and the mathematical structures here. I would explain the physics side as much as it's mentioned in the book, but I don't know anything actually more than that. Okay. Okay, so let's start. This is actually the first example of a PDE we are studying in this course. Here we are studying something like a bar, or what is called a rod. Suppose this is a bar or a rod, a metal bar or something like that, something which is a heat conducting material. So suppose this is a heat conducting material. Okay, so for example, if this point is very hot and if this point is very cold, the temperature and the heat would move from this point to this other point. Okay, so that's, in that sense, this is a conductive material. Okay, so there are the idea is that we want to see if we start from some configuration. So some points are hot, some points are cold. We want to see how the heat and temperature would move along this bar, and how it would look like after a while. For example, how does the flow of temperature would look like? These sorts of questions. There are some simplifying assumptions here. For example, we would assume, if you look at the cross section of this thing, we would assume the temperature at different points in same cross section are equal. So at each cross section, if I show this axis with x, at each point X naught, if we look at the cross section, it has some specific temperature. The temperature at different points we are assuming are equal. And this assumption makes sense if this rod is quite long, okay, and the diameter is not very large. So if we assume it's something like this, different points in a cross section are very close to each other, right? And because they're very close to each other, it makes sense to assume their temperature is almost equal, right? So that's one assumption we are going to have here. Okay, let me sketch this figure again. We have the x-axis here, and we also have, there is also another axis, which is time. Time is, of course, I'm not going to draw that, but time is also passing on. Okay, the basic idea here to write down an equation is a very important law in physics, the law of conservation of energy. So if we look at small part of this rod, for example, let's say here we have a point X, and we move forward by delta X to get to another point X plus delta X. Let's just look at that specific part. So let's focus on that. Let's say this is X, and this is X plus delta X. So the point is that from each part of this, and then it continues, right? I'm just focusing on this part. From these two cross sections, some amount of heat or some amount of energy might enter, right? So there is some amount of energy, the amount of energy which enters to this area. For example, it might come from here or it might come from here, right? There's some amount of heat which comes inside. There is some amount of heat which leaves. Maybe it's better to say heat because we're writing down the heat equation. So there is some amount of energy, the amount of heat which leaves. Okay. Now there are two other things which might happen. There's some amount of heat that might just stay there. So the amount of there might be some amount of heat which might go outside. There's some amount of heat which might stay there. It's like thinking about this place as storage, right? So the amount of heat which enters seems to be, it seems it should be equal to the amount of heat which leaves plus the amount of heat which, the heat which is stored there, which stays there. There is one more factor which, since I'm not a physicist, I don't understand it very well, but we can just assume as our model. So we can assume because, well, when you have a conductive material, apparently when things, molecules and stuff goes around because of resistance and other things, there might be some generated heat at some points too, okay? For example, if you think about it as a wire, it might become hot just because there is flow in it, there is heat flux in it. So the generated heat in this region. So there are some things coming inside. There are some amount of heat generated here. This quantity should be equal to the amount of heat which stays here plus the amount of heat which goes outside. And that would be the conservation of energy. Or, well, here it seems it's conservation of heat for us. Okay, so this this kind of equality is, this law is kind of the base of writing down our equation. I should say, although in this book at least, this equation introduced using this physical physical experiment, this phenomenon in physics. This equation appears in a lot of other places, especially in mathematics. For example, you would see this equation when you're studying geometry and analysis all the time. So it's just one example for introducing an important equation. Okay, so let's say this is our rod here again, and this was the point X, and this was the point X plus delta X. Okay, now we are going to introduce a quantity, which we show that with Qx, which depends on the point X, and time t. This is the heat flux or heat flow at the point X at time t. So this shows for any point you choose, it shows how much heat is going, how much heat flow we have, how much the heat is moving around. So if this quantity is positive, it's just a convention. It means we are assuming the flow is going to, the heat flow is going to right. The heat is going to right. If it's 0, it means at that point the heat doesn't going anywhere. We are kind of in a steady situation. It's not going to right or left at that point. And if it's negative, we mean the heat is going to left. For example, suppose the right part is very hot, the left part is very cold, and the heat would go from right to left. We show that with Q being negative. That's how we would understand that. Okay. And this Q is kind of, this Q or this flux is defined by, is kind of defined on the unit. So for example, if we have this flow is Q, if this surface here, if we look at this cross section, this surface here, if the area is A, if this area is larger, we can have more amount of heat going from one direction to the other. In contrast to the case where this cross section is very small, we can have less amount of heat going from one point to the other. So the amount of the total amount of flow which we can have, if this surface, the area of this surface is A, the total flow, the total heat flow, which we can have at some point X, from left to right or right to left at the time t would be A times Q. So this Q is kind of defined per unit. So if our area is 2 times that another area, the potential heat flow which we can have is 2 times that one. Okay, any question here? Okay, great. Now, here in this bar at this point X, suppose the area is A. Another assumption we are going to have is that at all points, the cross section is the same, okay? This doesn't move, it doesn't change. The cross section is something constant. So the area at both points X and X plus delta X is equal to A, right? So the amount of heat which is going to come inside this region and the amount of area which goes out of this region is related to these points. So this is our region. And here the heat flow here would be Q of X and T times A. The heat flow here would be Q of X plus delta X and T also times A. If this quantity here is positive, it means the heat is coming inside our region. If it's negative, it means the heat is going outside of our region. Also, this quantity here, if it's positive, it means the heat is going out of our region. If it's negative, it means the heat is coming inside our region, right? So writing down the conservation law we had, we remember the amount of heat which enters plus the generated heat is equal to amount of heat which leaves plus the amount of heat which is stored there, right? And therefore, if I take the amount of heat which enters and leaves to one side and the generated heat and the heat which is stored to the other side, we would see the amount of heat which enters minus the amount of heat which leaves is equal to the amount of heat which is stored there minus the amount of generated heat. Now the left-hand side, the thing we have here above, the amount of heat which enters minus the amount of heat which leaves is equal to, well, what we had earlier, A times Q of X and T. This is the amount of heat which enters minus the amount of heat which leaves. Well, if they are positive. If this one is positive, it means we are gaining it. If it's negative, it means we are losing it. If this one is positive, it means we are losing it because it's in our figure here, it's related to this one. So if this one is positive, it means heat is going outside. So we should consider that with negative sign. It's like losing heat. So this quantity on the left-hand side is equal to the amount of heat which enters minus the amount of heat which leaves. Now, there is amount of heat which is generated. Let's use G to show how much heat is generated at each point X, okay? So G of X means how much heat is generated at some point X, at each point here. Not at this, at any point at actually. So maybe I should just show that with G, not G of X. G shows how much heat is generated at each point. And this is proportional to volume, right? If we have larger region, the amount of heat generated in that region would also be larger. Whereas if you have a very small region, the amount of heat generated in that is small. So the total heat generated in our region would be G, which is defined for the unit, times the volume of our region. But the volume of our region is A times delta X, right? The volume would be A times delta X. So it would be G, A, G, delta X, right? We should consider that with negative side, actually. We have plus the heat stored. What is the amount of heat which is stored here? Well, that depends to a lot of different things. So what is the amount of heat stored in that region? Well, this quantity depends on a lot of different things. So of course, if we have a larger volume, we would have more amount. It's possible, there's the potential of storing more heat. So first of all, it's proportional to the volume, which is again A times delta X. Another thing which this thing is proportional to, apparently, I'm not a physicist, I guess you should ask an engineer or a physicist, but as the book says, when we have higher density, we can store more heat in that region. So if we show density with rho, If we multiply that, we should multiply that by rho because it's also proportional to density. If you double the density, if it's something more dense, you can store more heat. It's also related to something else which is shown in the book by C. It's called the heat capacity. It's related to the material of this bar, this rod. Some things like water, or I think a water or another object like air, their heat capacity is different. Some of the objects they can store a lot of heat, some of them can't. This C describes how much this specific thing we have here, object we have here, can store heat in it. Okay, and the final thing is that if we store heat at some point, the temperature would rise, right? So there is one more thing. If we storing heat in a region would cause would raise temperature. So if I show temperature at each point here with U, the temperature, suppose U of X and T is the temperature of the point X at time T. If we have heat stored there, the temperature should rise. So the heat store is proportional to the changes in temperature, because if you have heat stored there, the temperature should rise. So it's also proportional to the changes of temperature, derivative of temperature with respect to time. Okay. So if I go to the previous slide, here, this heat stored here is equal to A delta X times density times heat capacity times the changes in temperature. Okay, that would be our equation. Okay, is there any question here? Although I don't think if you have really a physics type of question, I don't think I would be able to answer. These are just the basics of, you know, as a motivation to write down the equation. What we would mostly spend time on is just solving the equations. But anyway, so the equation would be, if I take the terms to right and left, the equation would be A times Qx and T plus A delta X times G. This is the factor we call that generation rate. How much heat is generated at each point is equal to AQX plus delta XT plus A delta X rho C, derivative of U with respect to C, with respect to T. Okay. So I would take terms which have Q in them in one side and take everything to the other side. AQ of X and T minus AQX plus delta XT is equal to A delta X rho C, derivative of U with respect to T minus A delta X G. One interesting thing you can see here in this equation is that everything has factor A in it, the area of the cross section. And you can cancel, you can divide the equation by A. So A would disappear. So it seems A affects everything, but at the end it doesn't affect anything. It cancels out. So now if we divide the equation by delta X, we would get q of x and t minus q of x plus delta x and t divided by delta x is equal to rho c delta u delta t minus minus g. That's what we are going to get. Now, I prefer to multiply everything by a -1. So I prefer to multiply everything by -1, since if I do that, I would get q of x plus delta x and t minus qx and t divided by delta x is equal to minus rho c delta u delta t plus g. Now we can take limits from both sides of the equation. So take limits from the equation and send delta x to 0. Now, the interesting thing here is that right-hand side is independent of delta x. There is no delta x on the right-hand side. So the right-hand side does not change. Right-hand side is minus rho c changes in u with respect to t plus g. The left-hand side, well, that is the definition of derivative, right? Derivative with respect to x. So that's the derivative of q with respect to x. So that's the equation which we would get. Let's call this equation star. So the point here is that this is an interesting equation. However, here we have two unknowns. One is the function u. We don't know what u is. The other one is the function q. We don't know what q is too. And having one equation and two unknowns, it's not really possible to solve. So we need a second equation. So we need a second equation, right? So what is this second equation which we are looking for? This second equation is something called Fourier, if I remember it correctly, Fourier's law or something like that. It's not related to Fourier series, it's just the same person. And this law says q is equal to minus a constant. We show that with kappa or k or kappa times partial u partial x. What does it say? It says if you look here, if I look at this pipe we had, if at some point is hot and some point is cold, if I show temperature with a graph here, so if this is temperature, if this is hot and this is cold, the graph would be like this, right? It's hot and then it's cold. So in that case, what would be the direction of heat? What would be the direction of heat flow? Then the heat would go from hot to cold. So this would be the direction of Q, right? The direction of Q is towards the place which we have the temperature, we have less temperature, right? So this tells us when at the points which temperature is lower, Q is pointing towards that direction. So for example, if the temperature is like this, is like the case here, it's going down. Since the graph is going down, the temperature is going down, the derivative of u with respect to x is negative, right? It's going down. But because q is going to right, our convention was telling us when q is going towards right, q is positive. On the other hand, if the graph of u was the other way around, if the graph was like this, here was hot and here was cold, then partial u partial x would have been positive because the graph is increasing. Then the direction of q would have been the other direction, but because it's towards negative, by our convention, q would have been negative. So if one is positive, one is negative. If one is positive, the other one is negative, right? And so one of them should be something like something times minus of the other one, and that thing is constant. So this is called Fourier's law. Here, partial u partial x is negative because the graph, the function is decreasing, right? When a function is decreasing, the derivative is negative, and the function is increasing, the derivative is positive. Okay. And so I'm, again, about the physics aspects of this equation, I do not know much more. But again, here we accept that as a fact. Now, if we plug in this thing in the equation we had earlier, so we had this equation, we had partial q partial x equals minus rho c partial u partial t plus g. And then that was the star equation. And now we have a second equation which says q is equal to minus a constant partial u partial x. Now, if we plug in this equation into the other one, so if I plug in this thing here, I would have partial q partial x, but q itself is equal to minus k partial u partial x, would be equal to minus rho c partial u partial t plus g. Okay, now k is a constant, so the left-hand side would be equal to, this is equal to minus k, the second derivative of u with respect to x. Okay, and we can divide everything by k. So if we divide everything by k, we would get, and multiply by -1, we would see the second derivative of u with respect to x plus, I will bring g to the left-hand side too. It would be equal to rho c over kappa times partial u partial t. Now this thing here is a constant. It is a constant. We show that with k. So we would get the equation, the second derivative of u with respect to x plus g over kappa is a constant k times partial u partial t. This is the PDE which we are supposed to think about. As I said, this PDE also appears in mathematics in many places, independent of physics, this sort of equation. So what sort of equation is it? You have a function. The function depends on x and t. And the second derivative of the function plus a constant equals another constant times derivative of u with respect to t. This sort of equation in general. For example, in a lot of places in geometry, you would also see this equation. Okay. Now, well, solving this equation would be slightly different. It wouldn't be similar to the previous equations. The reason here is that this is not an ODE anymore. This is partial differential equation, because here we have derivatives with respect to x, and we have also derivative with respect to t. And that's a new phenomenon. We didn't have this before. So we should find new ways to solve these sorts of equations. Okay. So one simplifying assumption to start to work with is that let's assume this generation factor g is equal to 0. So in that case, we would have this equation. The second derivative of u with respect to x is equal to 1 over k, just a constant, times partial derivative of u with respect to t. Suppose this region we have starts at x equals to 0 and ends at some x equals to a, okay? We want to, so the idea is how can we solve this equation? Okay. So there are different ways we can think about this equation. We can try to see if we can find any solution, right? We can write down a few examples. So as some sort of trivial example would be like this. Suppose u is a function of x and t. Suppose it can be written as sum of two functions, okay, which one part is just a function of x. Say, let's show that with f1. And the other one is just a function of t. Okay, that's not just assumption. Let's assume we can write down this function u as sum of two functions. One of them is a function of x and the other one is a function of t, okay? So this would tells us that the second derivative of f1 with respect to x, because it's a function of x, maybe I should still write down the second derivative of f1 with respect to x would be equal to 1 over k derivative of f2 with respect to t, right? Because when I take derivative of u with respect to x, the second term would be 0. And similarly, when I take derivative of u with respect to t, the first term would be 0. So it's very easy actually to construct these sorts of kind of solutions. One extra simplifying assumption I can have can be this. So this was just assumption. Suppose, let's have another assumption. Suppose these two, not they're only equal, but also they're equal to another constant c, okay? So it is just, again, an assumption. I'm assuming these two quantities, they're equal to each other, and also they are constant. They're equal to another constant. Okay, what does that tell me? So if that's the case, it would give me two other equations, right? One equation would be the second derivative of f1 with respect to x is equal to constant, and derivative of f2 with respect to t is constant. Well, let's integrate both sides. It means the derivative of f1, well, the second derivative of f1 is constant. This is derivation with respect to x. So f1 prime, if we integrate both sides, is equal to a constant times, say, x, right? Plus, well, plus another constant. Let's show that constant with d. And let's integrate again. Therefore, f1 is equal to cx squared over 2 plus dx plus another constant e, right? And here, f, its derivative with respect to t is a constant. So f would be that constant times t plus another constant. Let's show that constant with h. This gives a solution to the equation, right? What was u of x and t is equal to f1 plus f2. That's how we assume this function is. So it would be equal to cx squared over 2 plus dx plus ct plus a constant e plus h, right? That's just another constant. E plus h is just another constant. Let's show that other constant with b. So this is indeed a solution to the equation. This is one solution. This is one solution. to the equation which we had. I think it was 1 over Kc, right? So it would be Kc plus Kh. It would be Kct. So this is one solution to the equation we had, but we can just plug that into the equation. But the question, the more interesting question is that, is there any other solution? Is it all, or is there any other solution? Or did we find all solutions to this equation? So that's our question for now. Let's have 10 minutes break. We can come back and continue from here. You can also think to see if you can find any other solution to this equation. Great. Yeah, I see. Yeah, that is correct. So this is not 1 over K. This was my mistake. This is K. So it would be C over K plus, well, anyway, plus a constant. And later here in the solution also would be C over K times T. Okay, let's continue. So do we have any other solution to this equation? Does anyone have any idea how we might find another solution to this equation? Okay, so the idea to find another solution is kind of similar to the first one. Okay, there is a guess. I see. What is y? We only have x. What do you mean by y? So we have x and t, so maybe you mean e to the minus x squared t, huh? Is that what you have in mind? Well, you can work on that, and if it gets to some, yeah, if it gets to some result, you can share it. That would be interesting. So as you can see, we kind of start, well, we are in the level of just guessing the answer. So the first way we solved this equation was by just saying maybe the solution can be written as sum of two parts, which one part is just function of x and the other part is just function of t. Now, the other kind of approach you can have is very similar. You can say, maybe I can write down the solution as two parts, where one part is the solution of x, the other part is the solution of t, and this function u is the multiplication of these two things. Okay, we can try that, you know, any sort of idea you come up with, we can try that to see if that works or not, or if it works, it is helpful or not. So let's just assume that. So suppose we can write down u as multiplication of two functions. One is a function of x, and the other one is a function of t. So our equation says the second derivative of u with respect to x is equal to k derivative of u with respect to t. So let's do that. So what is the second derivative of u with respect to x? Well, if we take derivative with respect to x, this part, f2t, that part would be independent of x, so derivative doesn't do anything to that derivative with respect to x. So we would get f2t, it's just like a constant, the second derivative of f1x with respect to x. And well, completely similar to this one, derivative of u with respect to t would be f1 of x, derivative of f2 of t with respect to t. Okay. Now, if we plug in these two things into our equation, we would get f2t, the second derivative of f1 with respect to x, dx squared, is equal to k, the constant k, times f1x df2 dt. I should say, sometimes I write d dx, sometimes I write partial x. So this notation is preferred. Sometimes I don't pay enough attention. Okay, so here I expect you to actually guess what would be the second step. What can we do with this equation? Although we have not worked with PDEs in this course yet very much. We have laid the backgrounds for that and the basics, but this is the first time. But I still expect you to know what we can do with this one. So do you have any suggestion here? What can we do? See here, there are two variables. We have variable t and we have variable x. Is there any suggestion on what would be the next step? That is correct, yes. We should try to separate the variables x and t. That is exactly what we should do here. So I would try to take the x variables to one side and t variables to another side. So I would divide everything by df2 with respect to t, and second derivative of, I would divide everything by f1 and f2. So I would get, so here we have f2t, the second derivative of f1 of x with respect to the x squared equals kf1 of x df2 dt. So if I divide everything by, divide the equation by f1 of x, f2 of t, we would get this. The second derivative of f1 of x with respect to x over f1 of x would be equal to k times the derivative of f2 with respect to t over f2 of t. Okay. Now, again here, this is very similar to the previous case. I can say, I'm assuming this is a constant. Does anyone know why here I can assume this is equal to a constant? There is a reason why I'm assuming if these two things are equal, they can be equal to a constant. We did this in the previous solution too. Why is that? Why can I assume this is equal to a constant? No, this assumption is not after a very long time. No. So let me give you, well, this is a function of t. So let me give you one more hint. This part, the whole thing is a function in one variable. That variable is x. This part, all of it is a function. The variable is t. So they are supposed to be equal. That is not possible. Do you agree? I mean, one of them is a function of x, the other one is a function of t. How can that be equal? Unless the result on the right-hand side, everything has kind of canceled out, and at the end there is no x in it, right? And on the right-hand side, which is a function of t, everything has been canceled out, and at the end there is no t in it. If that wasn't the case, if there was still some x in the first quantity, there was still t in the second quantity, they couldn't be equal. Does that make sense? Yeah, great. Okay, if that makes sense, yeah, that's great. So these two things, we should assume they are equal. And that's what we did in the previous part too. When we had this, we wrote them as sum of something plus something else. We saw they should be equal. Yeah, that is correct. You are going towards solving each equation. Yeah, you're certainly right. So now we have two equations. One tells us, well, they're equal. So the first one is equal. And then the second one should be equal to this constant. And now this gives us two ordinary differential equations. So the first one says the second derivative of f1 with respect to dx squared is equal to cf1 of x. Everything is about x. And the second one says the derivative of f with respect to t is equal to c over k f2t. So as you can see, both of these things, 1 and 2, both are ordinary differential equations, right? Each of them is with respect to just one variable. In one of them, we have derivative with respect to x. In the other one, we have derivative with respect to t. And each of them is a homogeneous equation. We know how to solve these equations, right? So we started with the partial differential equations. Using some modifications and some assumptions, now here we have two ordinary differential equations, okay? That is the idea here, okay? Okay, let me see. Great. Okay, is there any question here? Okay, so we can solve these two. So let's look at the first one. The second derivative of f1 with respect to x is equal to a constant times f1. Let's start with solving this one. You can start thinking about this one. There's a comment in the chat. Yes, yeah. Okay, let me go back. So the reason I'm assuming they are constant is that one of them, this one, it's only a function of x. I assumed f1 is a function of x. So its second derivative is a function of x. If I divide that by x, is a function of x. So this thing is just a function of x, no t. So this is a function of x, something like e to the x, cosine of x, something like that. The other one, this one, f2, I'm assuming is a function of t. So its derivative with respect to t is a function of t. If I divide that by f2 is a function of t. So the whole thing is a function of t, and there is no x in it, right? Now these two things are equal. One of them is a function of x without t. The other one is a function of t without x. How can they be equal? Well, they can't unless both of them are just constant. If there's x in one of them and t in the other one, they wouldn't be constant. They wouldn't be, equal anymore. Great. Yeah, that's great. So here we have a homogeneous simple ODE. What is the solution to this equation? What is f1? I guess you know, well, f1 here is a function of x. I think you know how to compute these, the solutions to these homogeneous equations. So if we want to solve this thing, we should look at its characteristic polynomial. It would be m squared equals, yeah, m squared would be equal to c, and therefore m would be equal to, well, okay, here we have, that's the thing. So here, c might be positive, might be negative, and these two cases would be different, right? So if c is positive, we would have two real solutions. If c is negative, we would have an imaginary solution. So let's suppose c is positive. So this is another assumption. We can consider different cases. Let's start by assuming c is a positive number. So we would have two solutions. m1 would be square root of c. m2 would be minus square root of c, right? So if c was 0, we would have a different case. If c was negative, we would have that complex case. Okay, so we would have, what are the solutions? It would be a constant, say c1 e to the square root of c x plus c2 e to the minus the square root of cx. We are here assuming they are positives. They are positive, so this makes sense. If c was 0, that's one case, right? This would be one case. If c was 0, the second derivative of f1 with respect to x would have been 0. So derivative of f1 with respect to x should have been a constant. So f would have been a constant c1 times x plus c2. That was the other case. There was, if c is 0, there's no reason even to write down the characteristic equation. And if c was negative, what we would get there? If c was negative, we would have the second derivative of f1 with respect to x equal to a negative number times f1. So the characteristic polynomial would have been m squared equals to c, where this is a negative number. So m would be equal to plus minus I squared root of c. So here we only have the imaginary part. So what do we get? We would get cosine of this thing and sine of this thing. We would get, let's say, c1 cosine of square root cx plus c2 sine square root cx. This would be the solution in the imaginary case. So this is, in the case c is, well, sorry, this would be minus c here because it's negative. So it would be minus c under the radical. Okay, great. So here, so we have these three solutions. One is when c is positive, we have e to the alpha x. When c is 0, we don't even need that. When c is negative, we have cosine and sine. So remember, in general, just as a reminder, in general, if the solutions to the characteristic polynomial are complex numbers of the form alpha plus I beta, the solutions were, what was it? E to the alpha x cosine of beta x and e to the alpha x sine of beta x. So here for us, alpha was equal to 0. So e to the alpha would be equal to, alpha x would be equal to 1. So we just had cosine of beta x and sine of beta x. So you see here, we compute f1, and that's it. We have f1, whatever it is. And then we can go to compute, we can continue to compute f2. What was the equation for f2? So the derivative of f2 with respect to t was equal to k over c equal to f2, I guess. That was the equation. So what is the solution to this equation? What can I do here? Well, probably you remember df2, this is the separation of variables. Is k over c dt. We can integrate both sides. So if we integrate both sides. The left-hand side would be Ln of absolute value of F2 equals K over C times T plus another constant C1, and therefore F2 would be another constant I showed with capital C, e to the K over Ct. So we have F1 and F2, and their multiplication would be a solution to the equation. So this is another solution. This is not equal to the previous solution we had. The previous solution we had was the sum of two solutions. Here I have multiplication of two solutions. Is there any question about this process? Did I make a mistake with the constant again? Just a constant. Let me see. What was the equation? It was C over K, huh? I see. C over K. So this discussion here shows us that this U of X and T can have different solutions. So for example, one solution was of this form F1x plus F2x for some X1 and F1 and F2. We solved it in a different way. We got a different solution of the form F1x times F2t. And they are not really equal. They're different. So different techniques gave us different answers. And that's not very satisfying, actually. So usually the idea is to add some, if you specify some initial or boundary conditions, you would end up with the explicit solution. So as you can see here, we did it with two ways. We got two different solutions. If you do it any other way, maybe you get another solution. Therefore, there are so many solutions to this equation. So there are ways to add conditions to specify exactly which solution you're looking for. So there are two sorts of conditions here. One of them is one family. They're called boundary conditions. And the other one is called the initial value conditions. Initial value conditions. So what is the story here? So for example, we have this bar here. We are studying a function u defined here. We can have extra assumptions. So we want to find u at any point x and any time t. We can assume that at time t equals 0, a specific function is given. So maybe this is a very appropriate condition that find all functions u of x and t such that at t equals 0, u of x and 0 is equal to a very specific function. I would show that with f, say f of x. That doesn't depend on the parameter t anymore. So an initial value condition would be giving what the solution we want at time t equals 0 is equal to this given f of x. So this f of x is given. So that is one sort of solution. Okay. One sort of condition. Another sort of, so this is the initial value condition. Another sort of condition, there are boundary value conditions. So in this bar, we are looking for a function u of x and t. Suppose somehow with some process, we fix the value of u here to be something constant. So for example, if it shows temperature, suppose that part is connected to ice. So that temperature there is constant. Okay, so here if x here is 0 and x here is a, we can assume u of, for example, 0 and t at all time is something constant, Let's show that with t naught. And u of a and t is also always constant t1. So these, you can think about these two parts, x equals to 0 and x equals to a, as the boundaries of the thing we have, and the assumption of these two parts are kind of the boundary conditions. The conditions of those two parts are boundary conditions. Okay, that's one sort of condition we can have. So this condition saying u at some point x naught and t being something given. So in the previous slide, x naught was 0 and a. Maybe rather than 0 and a, somehow you want to fix the value of u at some other x naught to be something constant, for example. This sort of condition to specify at some x naught or at two or at few points, u is something given, is called the condition of first kind. And this doesn't have to be even constant. You don't need even to say u at this point is constant. You might want to change it through time, but this is given. You know, it's not part of the question, it's part of the data. Again, if it's temperature, suppose up to some point it's connected to ice. After some point you connect that to something hot with a given temperature, so it would have that temperature. So anyway, it's part of the question. So we show that with alpha of t. So this kind of condition is called condition of first kind, or also known as, well, if I pronounce his name correctly, Dirichlet condition. Okay, that's one sort of condition. Another sort of boundary value, so these are boundary value conditions. Another sort of boundary value condition is that rather than fixing, for example, u at some point to be something given, rather than that, you can do something that, for example, u here would not change in direction of x. In another sense, you can do something, connect this part, for example, to some material which which is not conductive anymore. So if you like connect this to something which is not conductive, the temperature wouldn't move from there anymore. So in another sense, if u was our function which shows the temperature, in direction of x, you can do something that the derivative of u with respect to x at that given point does not change. For example, it's 0. Or if it changes, you can assume it changes in a given way. So we are assuming this is given with some function beta. So I don't know if these things make sense in real world, in physical sense, but mathematically, they appear in a lot of math questions. So sometimes you have an assumption on function u at some points. Sometimes you have an assumption on the derivative of this function at some points. Okay, so this sort of conditions, the second sort of condition, of course, they are called the condition of second type or second kind. And similar to the first one, which is named after Dirichlet, this one is named after von Neumann. I think his spelling is something like this. Von Neumann was a mathematician who was almost doing everything, and he almost knew all fields of mathematics, physics, computer science, etc. He was a very interesting scientist. Okay, so these are two sorts of boundary value conditions we can have. Okay. Is there any question here? So sometimes, rather than fixing value of u at some point or its derivative, we might want to fix a linear combination of them. So another sort of boundary value condition can be like this. Suppose a linear combination of u at some point x naught and its derivative at that point is fixed, is given. So this is again a function which is given. This is part of the data of the solution. This condition is called the third type condition. It's named after Robin. It's called Robin condition. This is another sort of condition. There is a fourth type of condition, sometimes known as Newton's law. Again, here we have this bar here, and say this end is connected to another place. So suppose this is connected to some other material here. Suppose this here is, you have air here, and it's kind of it's connected to that thing, right? And the point is that when we are in this situation, we would still have flow. For example, if U was showing temperature, we can have heat flow going out or coming in. If we show that with Q, that Q is well, that Q depends on how much temperature differs between, for example, the air and our bar at this point. So if the temperature is, the difference in temperature between air and our bar is a lot, at this point, we can expect a lot of heat going on or coming in. But if the temperature is almost the same, we expect the heat wouldn't go out or come in. So it's proportional to the difference of the temperature. So if this is the point A, the temperature at the point A and T, minus the temperature of the air at time T. Let's say this is the temperature of that. So if it's proportional, it's actually equal to that times something. We show that something with T. Here we assume that T is a constant. Okay. So if you remember again, we had something called Fourier's law, which was saying minus kappa partial U partial X is equal to Q. It was related to the fact that if the function U is decreasing, temperature is going down, Q would be in that direction. So if the derivative of U with respect to X is negative, Q would be positive. So they have different signs, and therefore Q should be minus partial U partial X times something else, which we assume that something else again is constant. Okay, and here, if we have air here, as the way we talked about, Q itself would be equal to, as we said, H times U of A and T minus T of T. Now, if we plug in this equation into this one, what we are going to get is that Q is equal to, this would be equal to, well, let's see. It would be equal to minus kappa partial U partial X. It would be equal to H U and T minus H times T at the time T. Okay, this is another interesting equation. Okay. Now, you know, in math, we have an object called torus, which looks like this, something like a donut. Now, if you have a cylinder, if you assume it's actually a solid torus, it's not just the boundary, but it's also the inside. It's like the solid donut. Now, if you have a cylinder like the ones we have here, if you can bend it, if you can bend this cylinder, if you can bend it enough, you can bring two ends next to each other and you can glue them. You can connect them and you can glue them and you would get something like this donut. Now, this was the point x equal to 0. This is the point x equal to a, right? This was the point x equals 0. Here, x is equal to a. Now here, the points where x is equal to 0 has become equal. It's glued to the point which was x equal to a. Now, if you study the function u on this thing, on this torus, if you are studying a function u, rather than on a cylinder, if it's defined on this solid torus, well, u because the point x equals to a now is identified, it's glued to the point x equals to a. So the function u at the point 0 and t should be equal to the function u at the point a and t, because they're basically glued together now. They're right next to each other. And then the derivative of u with respect to x at 0 and t should be equal to derivative of u with respect to x at a and t. Okay, these are sort of kind of the conditions on solid torus. Okay. So we can have a combination of these assumptions. We can have a kind of combination of these conditions, usually called mixed condition. So for example, suppose we have one of these bars. We write down the equation for u. Suppose g is also 0. So remember, in that case, our equation was, I'm still not sure if it's 1 over k or k. It doesn't really matter. It's just a constant. Some k, whatever it is, times partial u partial t. Suppose at this point, x equals to a, function u is fixed. So u of 0 and t is fixed. Okay. And suppose in the other one, this is not fixed, but it's similar to the other thing which we said it's connected to air. So that condition was this one, minus kappa partial u partial x is equal to h times u a and t minus t. And suppose these are boundary value conditions. Suppose also there is an initial condition, which says at time equals 0, u is given. When t is equal to 0, at each point x, u is given, and say it's equal to some function f of x. So this is a sort of equation which we should be able to solve. We have a PDE. The boundary value data is given, and the initial data is also given. Okay, and for a suitable kind of data, we should be able to solve this one. Okay, great. Is there any question here? Okay, if not, maybe it's a good place to stop, because the next step would be to consider the steady state condition and, well, starting to solve the equation, at least some sort of limiting form of the equation. So here we finished, this was the end of 2.1. It would be very good if you can review that one more time for our next meeting. If you have the book, take a look at the book at the section 2.1. On Wednesday, we would start 2.2. Okay, no question? If not, we can stop the class here.